Hello, so I made a solver for Minesweeper, and this video is just going to be me talking about it. There will be 4 small sections, so first of all, what are we solving for, what actually is our goal, then what method are we going to be using. This will be the main part of the video, this is what I want to talk about. Then there's some limitations and then also some example uses. So we'll get right into it. What are we solving for? We're trying to find the known mine locations or known safe cells in Minesweeper. I'm going to assume that you already know the rules if you're watching this. If not, then you can read about that elsewhere. But our goal is to take a game state like this. So we have some open cells, some closed cells here, and then from that derive what we know for sure about where the mines are and where there are safe cells. I'd like to explain that using trivial logic alone is not enough to solve it, and by trivial logic we're just saying if a number is next to only that many cells, then they're all mines, and if we have already found that number of mines, then the rest are safe cells. So this does find some, so we find this is a mine, these are mines and so on, but over here that is not good enough. And in case you don't see it, we're saying that this one says there's one mine in these two, therefore this 2 has to get a mine from here. So we know for sure that there's a mine here, but this trivial logic will not find that. So the most fundamental idea in my solving algorithm is the notion of sets or groups of cells. So that would just be like a collection of, so you could have this one, and this one in a set, and so on. And for each group we have a known maximum and known minimum number of mines in that set. And the initial step of the algorithm will be for each numbered cell to look at all of the closed adjacent cells and create a group from that, and both the maximum and the minimum number of mines will be set to that number. So for instance, this one, I know there's at least 1 mine in these 3, and I also know there's at most 1 in these 3. So it seems strange to have these set to the same value, but what will happen is we'll look at the intersection between these groups, so we have this one and this one, and then we can start to do logic to change independently the max and min number of mines. And I should mention that ultimately our goal is to reach either one of these 2 criterias. So we're saying if the max number of mines in a group is 0, then it means we can't have a single one, therefore every single cell is safe. Right, so if we have 5 cells and they have at most 0 mines in, they're all safe. And a similar case is saying if the minimum number of mines is equal to the number of cells, then we know they're all mines. So similarly, if we have 5 cells that contain at least 5 mines, then they're all mines, right? So this here is an outline of the logic that we're going to do. It does not cover everything, but I just want to communicate the core idea, and I think these points will give a very good idea for you. So we will compare every pair of sets. We won't actually need to do that, there's a small optimization that I might mention later. But from the sets A and B, we want to make 3 sets, and that will be the intersection, and then the 2 original sets, subtract that. So in this case we have the reduced 3 will be the 2 blues, the yellow as the intersection, and in this case the reduced 1 has a size of 0, so it does not exist. But this idea is very simple. The intersection cannot contain more mines than the entire set because it's a subset of it, right? So if we did have more in the intersection, there would be a contradiction, therefore it cannot happen. Secondly, we want the idea that mines can be pushed into the intersection even if we try and squeeze as many mines out of it as possible. So if we look at this 2 and these 3 cells, that would be the group for it. Even if we try to put as many mines out of the intersection as possible, like here, then we're forced to have at least 1 here. So the minimum of the intersection is 1. And we'll do this for both ones, and whatever minimum is higher will be our result. And finally, we can use this information about the intersection to make some derivations about the reduced sets on the side. So previously we learned that there's at least 1 mine in this intersection here, and therefore this cell is safe because this 1 is creating a group that says there's at most 1 mine in these 3 cells, and we know that there's at least 1 in these 2, therefore we can do some subtraction and find that there's at most 0 in this cell. And I know maybe the way I'm phrasing this is a bit like more complex than it needs to. We could just say, oh, there's at least 1 here, so there's 0 here, but this is what the algorithm's doing, and I sort of want to go over that. And as I said, there's a little bit more, but that should have given you a pretty good idea. I won't go over a full example because it involves many iterations where we derive smaller sets and then recompute the logic on those. But I just want to show you the idea with this 3 and this 4. So we're going to assume that we've already derived that these are mines, so this will be groups with only one cell in, with a minimum of one mine. So the 3 encompasses these cells here, this group, the 4, these 5, the intersection would be these 3. So even if we try to push as many mines out of the intersection as possible for this 4, we can get 1, 2, but that means that there's at least 2 in the intersection. And since we already know this 3 is now complete, so we know that this is safe. And this is nice because eventually this derivation will give us that these 2 cells are safe and this is a mine. You can sort of imagine it being impossible for it not to be, because this 4 would have its remaining 2 here, which would be invalid for the 3. So I hope that gives you a little bit of an idea of what's going on. While I remember, I'll quickly talk about the optimization with a hash data structure. So the idea is that we can store the index of each group, with the key being the cell coordinate. So I've not drawn on all possible groups, obviously, but there'll be, say, a group here for this one, and a group here for this one as well, that it will be a part of. So it will iterate through them, then look up the the indices of all of these groups, and then it doesn't need to compare ones that don't have an intersection. So G1 and G2 here, there is nothing that we can derive from just looking at these 2. And this is surprisingly a lot faster, because we still have to go through each cell, but we're not going to compare every single pair of sets that are not intersecting. And as promised, I'll go over some limitations to using this method. Both of these can be overcome by using enumeration or combinations. So using this set method, we cannot get the probability of a cell being safe. I've looked into seeing like how many sets it's in and what proportion of mines there must or can't be in that. But because there's some nuance to how these sets are created, it's not reliable, it's not usable, so it cannot do probability. And similarly, it cannot do so-called combinations. So sometimes there are just situations where you need to iterate through possible combinations to see if something is safe or not. I will take this site's word for it. It's from Minesweeper Online. This is the so-called beginner difficulty. It's 9 by 9 with 10 mines in. And I have a keybind set to be solving, so we know that these are safe. I'm trying to see if it's not finding anything, if it's missing anything that I see. But it appears to be getting everything. And sometimes we'll need to guess, but beginner, it should not be a problem. So now we're on to intermediate. This is 16 by 60 with 40 mines, so it's a similar density, but a bigger board. Wow, it's seeing more than me. That's pretty cool. I did not see that that was safe, but it knows that it is. Nice. So it can do intermediate sometimes. If we needed to guess, then it could not. I think we did, yeah. We had to. I manually chose to go here. Expert size, this is 30 by 16 with 99 mines in. Well, that's a good opening. That's so cool. It's seeing it faster than I do, which is good. Man, and here we have to guess. Ooh, where do we go? Damn. And then after we know this cell, we know the whole board. So it can almost do expert. Maybe sometimes it will do expert. So my final example is going to be this no guess board. It's 9 by 9 with 27 mines in, so it's very dense. This is where we start, and because of the high density, we should get some nice patterns. And this is where the example from earlier is from. And there we go. So that's quite cool in my opinion. I hope you enjoyed. Bye bye.